Hello everyone. This recording is to replace the lecture from Monday since there was some equipment issues in the classroom and I wasn't able to simultaneously record the lecture while I was giving it. So we did a bit of review on Monday, but I'm just going to jump in right where the last video left off, which is to take a closer look at the support vector classifier that we learned about last time. And here we've written the cost function that we minimize in order to learn the W vector and the B, the bias scalar. And typically when we have a cost function like this, like we did for multinomial logistic regression or linear regression, we set the gradient to 0 to see what we can learn about the parameters. So we're going to try that here. We're going to see what happens if we set the gradient to 0, and these are the optimal weights and bias that would give the gradient equal to 0 with respect to both the weight vector and the bias coefficient. And the reason we're doing this is we're going to see that there's a structure here that is going to help us understand a few things and that we can use a little bit later in the lecture. Okay, so to start, we want to take the gradient of j, or the derivative of j, with respect to b. So when we look at j up here, obviously this last term is not involved, and we have to figure out what to do about this. So we see that this is the maximum of either 0 or this other value. Okay, so when this other value is less than 0, then this maximum operation will choose 0, and in that case, b will play no role, and so the derivative of j with respect to b would be 0. Okay, so when does that happen? That's again when this term is less than 0, and that being less than 0 is the same as this yi, zi being greater than 1. Okay, so in that case, we're going to set this value alpha I to 0, and then the gradient term, as you can see, or maybe this term, as you can see, will go to 0. Okay, now let's think about another case, which is where this term is strictly greater than 0. In that case, the maximum here will ignore the 0 and will just give you this term. So in this case, we can see that the derivative with respect to b will be c times minus yi. Okay, and so that is where we get this. So for that particular case, we want the alpha I to be 1. In that case, when this is greater than 0, is when this term is less than 1. Okay, so we looked at the case where the second term is strictly less than 0, and we also looked at the case where this term is strictly greater than 0. Now there's a third case, which is when this term is exactly equal to 0. And that case is sort of tricky because it's not easy to take the gradient there. In fact, when this equals 0, that's when yi times zi equals 1. And if you go back to this picture here, let me erase this. In this picture here, you can see that when yi zi equals 1, you're right at this point, and you can see that this hinge loss is not actually differentiable there. The slope from the left is different from the slope, slope from the left is different than the slope from the right. So at this point, because it's not differentiable, we don't really know what form this gradient will take, and so we're just going to use a question mark for this alpha I. Okay, so it's a little bit strange that we're doing this. Essentially what we're trying to do is we're trying to take gradients of a non-differentiable function, and so not surprisingly, something breaks down. But still, even so, this is still going to be a useful interpretation as we see. Okay, so far we're able to take the partial derivative of j with respect to b. Our next task is to take the gradient of j with respect to w. And basically, we have to follow the same procedure. So when this thing here is strictly less than 0, then the maximum takes 0, none of this matters, and then the gradient is, with respect to w, is only going to be the gradient with respect to w of this term, and we can write this norm squared as w transpose w, and then see that the gradient of this will be 2 times w, the 2 cancels with the 1/2, and we just get w. Okay, so that's the case again when yizi is greater than 1, in which case alpha I is 0, in which case this whole term vanishes. Now the other case that's easy to analyze is when this is strictly greater than 0. In that case, the max goes away, and we can just focus on the gradient of what remains. So we're going to have c times the gradient of this with respect to w, which is going to be minus yi xi. So that's where we get this term with alpha I equals 1. Okay, because this case is when this term is strictly greater than 1. And then, of course, we still have the gradient of that. And then the last case is when this is, again, exactly equal to 0, in which case the gradient doesn't actually exist. So we write this expression with a question mark for alpha I in that case. Okay, so when we step back and look at this, even though we have this question mark, we can notice a couple things. So first of all, we know that at this optimal point, w star, we know that 0 equals this. So we can rearrange that to bring this term to the left-hand side and find that w star has this form. And so we know that a number of these alpha i's are 0. And for all those i's, such that alpha I equals 0, you can see there will be no involvement of the training data yi or xi in w star. Okay, so again, w star is going to be determined only by what we call the support vectors. The support vectors are the xi and yi such that this stuff holds. Or in other words, the xi such that this equality holds true. In the picture here, those are all the circled ones. So those are the ones that are either, so if we're talking about the red points, either they're on the edge of the street, or they're in the street, or if there was a red point all the way on the wrong side of the street, that would also be a support vector. And for the blue ones, we're talking about the ones that are on the edge of the street, in the street, or if there was a blue one on the wrong side of the boundary, that would be also a support vector. Okay, so this analysis, even though it's a little bit strange with the question mark, we do see that both the weight and the same holds true for the, let's see, can we see it with the B? Maybe not, but we do see that that the optimal weight vector is only determined by the support vectors. We also do see another thing that even though we don't know, we only know a subset of the alpha i's, this tells us something about the remaining alpha i's, that somehow when you multiply them all by yi and sum them up, you must get 0. Okay. We'll see this page come back a little bit later in the lecture. Okay, the next thing to talk about is an alternate way that the support vector classifier is sometimes written. So if you go to some textbooks, and I think maybe the Wikipedia page might be written like this, it might look a little bit unfamiliar at first, so let me try to explain it. So essentially the whole idea is to define this maximum of 0 or 1 minus yi, just define that as xi. So like when we are thinking about this whole thing, we're just defining this as xi. Okay, in that case, you get c times the sum over I of xi plus the norm squared. So here you go. C times the sum over xi plus half the norm squared. Okay, now we do have some constraints. As you can see when you look at xi, it's the maximum of either 0 or the second term. What that means is that it will never be less than 0, and it will never be less than this other term. So we can express that with two equality constraints. xi I is greater or equal to 0, and xi I is greater or equal to 1 minus yi, and this is the zi, and then it has to happen for all I. Okay, so this is just a different way of writing the SVC. If you solve this optimization problem, of course you get the same answer as the other formulation. One nice thing about these xi's is that they are interpretable. They are called slack variables, and essentially they measure how much we're violating the margin. And what I mean by that is, are we on the edge of the street? Are we in the street? Are we on the wrong side of the street? So in particular, when xi I equals 0, that is when you are not violating the margin. So in other words, if we're in the blue class here, that means these points, they are on the correct side of the boundary and they're outside the street, so they would have xi I equals 0. The points that are right on the boundary or in the street, or if there's a blue point over here on the wrong side of the street, they would all have positive xi's. And the further they are in the wrong direction, the larger the xi grows. Okay, so if you're on this edge or in the street, xi will be between 0 and 2. If you're on the wrong side of the street, xi will be greater than 2. And if you're exactly on the boundary, then xi equals 1. And if it's greater than 1, that means you're on the wrong side of the boundary, so you would be misclassifying that training sample. Okay, so this is just another way to think about the SVC and these slack variables. Everything is true about the red ones as well. So for the red ones, these guys would have xi equals 0. This one that's on the edge of the street would have some positive xi. This one that is on the wrong side of the boundary but in the street would have a xi between 1 and 2. And if you had a red one over here, that'd be a xi greater than 2. Okay. So we've talked a lot about how to train the support vector classifier. Now let's talk about applying it to test data or classifying test data. So remember that once it's trained, we have these parameters b star and w star. And so if we're given a new test vector x, as we know with any linear classifier, what we do is we first compute the score z. And if z is greater than 0, that means we believe it's more likely that that the label is 1. And if zi is less than 0, we believe that it's more likely that the label is not equal to 1. So the other thing we learned a couple slides back is that we can write the optimal parameters as a sum over the training samples, where here we have the contribution from the ith training sample, and then these alpha i's tell us how much they're weighted, and we know that for some subset of these alpha i's, they can be 0. So we only use the support vectors. Those are the alpha I that are not equal to 0. Okay, so imagine now that I just plug this W star into this equation. Now we can get an equation for the score, which is actually written without explicit mention of the weights. You can see that it involves this bias coefficient, and it involves the training data, labels and vectors, as well as the test feature vector. And so here again, you can see that some subset of these alpha i's are equal to 0, and that means that the classification of that test sample also is not going to use those training points there. So one thing we can learn from this, or maybe when we compare it to the multinomial logistic regression or logistic regression classifier, is that the SVC tries to focus only on the more important training samples, the support vectors, whereas multinomial logistic regression essentially uses all of them. And so we can again see that here. So for any training sample such that yi, zi is greater than 1, this is not using those samples at all. It's just ignoring them. and it's only using the training samples that are on the left side of this boundary here. Whereas logistic regression, you can see it's putting some weight on all the training samples, even the ones that are easy to classify. The weight is small, but maybe when you have a lot of them, those things add up. And that is sort of the intuition, kind of trying to connect back to what we saw way back on this page with logistic regression, is when you have 100 training samples, then the weights we learn seem to make sense. But when you have 10,000 training samples, maybe a lot of them are easy to classify. Still, they are being used to come up with these somewhat crazy patterns for the weights. Okay, so maybe the SVC is going to do a good job because maybe what it will do is focus on the 100 hardest to classify samples and construct its weights only from those. Okay, so let's see. So that brings us to, SVC tries to focus on what's most important. That's the main thing here. Okay, next topic is how do we do a multi-class SVC? So until now, we focused on K equals 2 classes. What if we have more than 2 classes? You need a different approach. So we're going to take the same overall strategy as we did with logistic regression, which is the one versus rest strategy, which is to say that we are going to learn separate binary classifiers that tell us whether we're in, let's say, for these two, it's going to tell us whether we're in class 1 or not in class 1. The next one will tell us whether we're in class 2 or not in class 2. The last one will tell us whether we're in class K or not in class K. And so, once we have these trained, we can create a vector of scores, Z1 through ZK, and the largest element in this vector is the class. The index of the largest one tells us the class that we believe the training sample is in. Or in this case, in this equation, we're actually working, these are the training samples, and so this is for the ith training sample. You would look through and you'd find the index of the largest value, and you would report that as your classification guess. Okay, so the question now is, how do we train all these parameters? So one option is to separately train the pairs using the binary strategy. So in other words, we think about this as a binary problem, and we solve for B1 and W1. Then we freeze those, and we think about B2 and W2 as another binary classification problem. We design them, freeze them, and so on. And eventually, we get all our parameters designed, but they're not designed jointly. They're designed separately in each one of these pairs. Okay, so a different approach is to try to jointly train all the parameters together. When we were doing logistic regression, we called that approach multinomial logistic regression. In the case of the SVC, it's known as the Cramer-Singer approach. And this is what it is. It looks a little bit complicated. So here we have the sum over our training samples, but then now we have another sum over all the class label indices that are not equal to the ith training label. And over here we have an extension of the 2 norm of the W vector to the Frobenius norm of the W matrix. We saw something similar in ridge regression, so that part's not surprising. But can we make sense of this? So one thing we could do is we could try to see whether, for the K equals 2 case, whether this agrees with the binary classifier that we designed earlier. So in this case, when you have 2 classes, you still will be designing 2 pairs of bias and weights. You'll be designing B1, W1, B2, W2. So that's a bit different than, in the binary classification case where we can get away with just designing 1 pair. But anyway, maybe we can still show a connection. Okay, so we're going to focus on k equals 2 here. And just to make the derivation a little bit easier, we're going to index the yi labels as either 1 or minus 1. Okay, so now just copying down this sum down to here, let's take a look. So let's think about this sum. If we have, in the binary case, j not equal to yi, since there's only two possibilities for yi, there's only one possibility for j, right? So basically, and because of our labeling convention here, whatever yi is, j will be minus yi. Okay, so we can basically get rid of this sum and replace j with minus yi, and then we get this. Okay, so we can actually make a further simplification to realize that there's two possibilities. You know, yi is either 1 or minus 1, and minus yi is either minus 1 or 1. So it's possible to fix this yi at minus 1 here, and then actually bring the yi to the outside. So for example, when yi equals 1 here, this term, the negative zi1, will be here, negative zi1, and then the other one, positive zi minus 1, will be here, positive zi minus 1. Okay, so there's just another way of writing it. And then the very last thing we can do is notice that we have basically our two scores. We have the difference between the two scores. So the first score is going to be, let's say, zi1, b1, w1, transpose xi. And then the second one is going to be zi minus 1, b minus 1, plus w minus 1, transpose xi. When you take the difference between those two scores, you essentially get the difference between the two bias terms, b1 minus b negative 1, and let's define that as b. Then we can write that difference just simply as b here. Similarly, you're going to get the difference between these two weight vectors. Let's define that difference as w, and then that allows us to write things like this. And finally, when we look at this expression, this is exactly the expression that we would get for the case of our earlier binary SVC. Right? This whole thing basically had this form. Okay, so basically at the end of the day, what we see here is that, that yes, when k equals 2, there's a direct equivalence between what this is doing and what our binary SVC earlier is doing. But of course, the advantage to this approach is that it works for k greater than 2 as well. Okay, all right, so the last thing to talk about is how we implement this in scikit-learn. So not surprisingly, it's pretty easy and pretty similar to the other logistic regression classifiers that we've seen before. So we use this linear SVC approach. The word linear will be clear in a few more slides. And remember that in this method, we always have this C variable that we have to tune or choose. And what we know about C is that as C gets larger, we expect fewer support vectors, although there may be a point at which increasing C beyond that point does not reduce the support vectors because you've gotten to the minimum number of support vectors. Okay, so here's when we instantiate this linear SVC. First, we have to tell it what loss function we want to use. And interestingly, so the hinge function is the one that we have been discussing over these last few slides. Interestingly, that is not the default option for the loss in sklearn. The default option is actually the squared hinge. So let me try to draw that. The squared hinge would agree, at this point, it basically looks like a parabola, something like this. So this is the squared hinge. And they do agree on this side, they're exactly 0. But what's nice about the squared hinge is that it is differentiable everywhere, unlike the ordinary hinge. So when you have a differentiable cost, the solvers you use, the algorithms you use to minimize that cost can run faster, basically. So the advantage of the squared hinge is that if you use it, your solver will probably run quicker than with the regular hinge. Of course, notice that you are changing how everything works. This is not going to behave exactly the same as a regular hinge, and so the solution will be different. In my experience, it doesn't work quite as well as a regular hinge, but it's a little bit faster. So just for this experiment, since I wanted to use the regular hinge, I had to specify it explicitly. Okay. The next thing is here telling it what value of C to use. This is ideally something that we should be tuning carefully. So this is not a very precisely tuned number. And the final option is when we have data that has multiple classes, we have to tell it whether we want to use this Cramer-Singer approach or whether we want to use this one versus rest approach. Basically, the Cramer-Singer approach is going to be slower to run. My experience, it works a little bit better. These are faster to train, but work a little bit worse. Okay, so then once that's instantiated, then we can fit the parameters to the training data. Then we can do the prediction on the test features to generate our predictions of the test labels. Then we can look at the mean of this basically binary vector here, which tells us how often they agreed. That gives us the accuracy. And when we print out the accuracy, this is for the MNIST problem, it is 90.73. Okay, so if you think back to when we ran logistic regression a couple lectures ago, the value was approximately 0.5% lower. So the support vector classifier did boost our performance, but not by very much. So you might say, well, that's kind of disappointing. We spent a whole lot of time going through all this math and all this stuff, and at the end of the day, all we get is a 0.5% improvement, and we're not really still that much closer to 100%, which might be our goal. Okay, so it's true. It's a little bit disappointing, but the next thing we're going to talk about is how to bring in some additional ideas in with the SVC, and then we will get a huge performance boost. And that brings us to what we call the support vector machine. Okay, so until now, we have worked on this support vector classifier, and the whole design approach there was to basically to try to make a robust classifier that had something like minimum distance, maximizing the minimum distance from the classifier boundary to the different training features. And so when the features are linearly separable or nearly linearly separable, it turns out that this support vector classifier works really well. But when the features are not at all linearly separable, which is the case for MNIST, it works okay, not that much better than logistic regression though. So the strategy now is, can we do some feature pre-processing so that after the pre-processing, our new features are nearly linearly separable? And that is the idea behind the SVM. So we're going to use a feature transformation. We're going to take our raw features X, and we're going to apply some nonlinear mapping function phi to get new features phi of X. And the goal here is that the new features are going to be more, closer to linearly separable than the old ones. They still might not be perfectly linearly separable, or they might, but hopefully they are closer to linearly separable. That's not all. we're also going to do one thing to make this implementation run faster, and that's called the kernel trick. Okay, so this illustration down here is trying to illustrate the raw features here. As you can see, there's no way we can linearly separate them because maybe this is the best boundary and it's far from linear. But maybe what we can do is we can do some transformation that will bring us from 2 dimensions up to 3 dimensions. And after we do that transformation, now you can see we can pass a plane to cleanly separate the 2 classes. Okay, so here's the same idea with a little bit more detail. This is still a toy example, but imagine that I have this 2-dimensional data set here. So we have these red points there, we have some blue points here. And as you can see with these raw features, there's no way we can do a good job of linear classification. There's no line I can place which cleanly separates the red from the blue. Okay, so what about if I add one more feature that takes the first squared and the second squared? So clearly that is the squared radius from the origin. So in this case, the origin is here. And you can see that that third feature is just going to measure how far you are out from there. And what's nice about that is you can see that all the blue points have a small radius and all the red points have a larger radius. And so here's the picture after we do that, that embedding. So here we have a 3-dimensional feature space. We have x1, x2, x3. And now you can see that along the x3 direction, it's very easy to separate the red samples from the blue ones. And again, that's just because we're essentially thresholding the radius. Hey, so this is just one toy example that shows how it is possible to do this. Now, a pretty tricky thing is if somebody gives you a data set and you don't really know anything about the structure of that data set, how do you come up with this transformation? What is a good transformation? So we'll show later in this lecture some of the most popular transformations people use. But still, it's a good question, and it's actually the motivation for what we'll do in the next unit when we study neural networks. In that case, we will actually try to learn a good transformation from the data itself. Okay, but for now, in this chapter, we're going to use some pre-chosen transformations that tend to do well with a lot of different data sets. Okay, so stay tuned for that. Okay, so our idea so far has been to apply some nonlinear transformation phi to our feature vectors x. And so in principle, that's something you could do. You could just pre-process x. And so if you're going to do that, then when you do your SVC training, essentially it's the same equation before, except now where there used to be an xi, there's now a phi of xi. And that's for the training. And then we also saw this expression down here, which is what happens during classification. And this used to be xi, this used to be x, but now because we do this nonlinear pre-processing, we have phi of xi and phi of x. Okay, so the reason why we might not want to do this is that, as I mentioned before, we tend to increase the dimensionality through this feature transformation. And this is just a toy example where we increase it by one extra sample. In general, you might want to increase it by a lot of samples or a lot of dimensions, because you simply don't know what's going to work with your training data. So maybe you come up with all sorts of different nonlinear functions of the existing features, and then you add all those on, and you get a very long feature vector phi in the hope that some of your new features are going to be useful. So the trouble with that, number one, is that if you grow the number of features in phi, then you also have to grow the number of weights in W. And so that leads to complexity problems. Number one, computational issues, but it also leads to overfitting, because remember that the training size, the number of samples, is going to be fixed, but the feature dimension is going to be growing. And back in Unit 3, we saw that increases the variance. Remember there's the bias variance trade-off. That increases the variance, and when the variance goes up, we get overfitting. Okay, so it's not just enough to massively increase the number of features. We'd like to know if there's some other way around this. And there's sort of a further problem. What if I want to use an infinite dimensional phi? Now that might sound kind of crazy, because why are we talking about all of a sudden using infinite dimensional phis? But as it turns out, when we look at the actual method that's most popular, it actually does give us implicitly an infinite dimensional phi. So even though it sounds crazy, it's actually the most common thing to do. But from this direct implementation, there's no way to handle that, because I would need an infinite dimensional W in order for the dimensions of that to work out. And so basically, we're stuck. We can't handle an infinite dimensional W or infinite dimensional phi. And also, even for finite dimensional phi, we could have computational issues and overfitting. Okay, so fortunately, there is a way around this. It's that kernel trick that I mentioned before. So the first step to understanding that is to reformulate our support vector classifier in a different way, and it's called the Lagrangian dual form. So this might look kind of complicated, kind of unfamiliar. The full derivation of this is outside the scope of this course. If you're curious about it, you can find it in section 12.2 of this textbook. And these techniques come from a convex optimization course. So if you've taken such a course, then I suggest to take a look. It will probably make sense to you. If you've never seen that stuff, I don't know that it would make sense. But the other thing is that this is actually quite similar to what we saw a few pages back. Instead of writing this in terms of these lambda i's, if you write it in terms of replace each lambda I with C times alpha I, then when we go back to page 20, you get essentially the same equations. So this is like our C, this is like our C alpha I that plays the role of lambda I, and so on. So a lot of these equations show up back on this page. Okay, so anyway, so if you accept that this is another way to do it, essentially what we've done is we've transformed the problem into, instead of learning weights of dimension d and a scalar bias, we are now learning some parameters lambda of dimension n. So n is our number of training samples, right? And the number of training samples is completely disconnected to the dimensionality of the features d. So that allows us, in principle, to not really worry about how many features we have. So here we have, our cost function. Here we have an equality constraint. Here we have two inequality constraints. So maybe you can remember a rough approach to how to handle this back from our optimization chapter. Turns out that this is a convex problem, so this can be solved with the right algorithm without any trouble. Let's suppose that somehow we've done that. We've solved for these lambda weights. Those are all you need to do the classification. So down on the bottom of the page here, if you're given these lambdas, you can compute your decision y hat simply by computing this quantity. As you can see, it depends on the training samples, it depends on the test vector, depends on the lambdas you learned, and also this b star, but the b star is something that you can also compute based on the training samples and the lambdas and so on. So the point is that if you take this dual approach, you never actually need to compute the weight vector. Now, if you wanted to compute the weight vector just to know what it is, that's certainly possible. This is the equation for the weight vector. This is the equation for the bias term. This I star is any index of a support vector, basically. So this is, again, though, it's totally optional. You never need to compute these to do the classification. Okay, so this is just a different approach to solving the SVC training problem. But what this does for us is it allows us to avoid ever computing the weights, and therefore, if we are interested in like an infinite number of weights, that's great. There's nothing infinite in this problem. Okay, so the way that we wrote this problem was just on the raw features. Okay, this is just another way of solving the SVC. But now imagine that we have these transformed features. And so what I'm going to do is on the previous page, every time I see an xi, I'm going to replace that with phi of xi, or every time I see a x, replace it with phi of x, and so on. So, and now, this is, if you had a particular phi in mind that you wanted to use as your transformation, you could solve it this way. And as you can see here, these terms are scalars, right? So the main difficulty, if phi is high dimensional, would be computing these inner products. But as it turns out, you don't necessarily need to compute things that way. In fact, what we want to do is you want to just think about this as a function of xi and x. Similarly, this is a function, we'll call it kappa, of xi and xi star, and so on. This is another function of xi and xj. Okay, and this function, we're going to call it the kernel function. And once we think about this in terms of the kernel function, we never need to think explicitly about a phi. In other words, if we just define the kernel function directly, then we never need to think about the phi that is actually being used. Maybe there is some phi being used, but it doesn't matter. All we really need is a good kernel function. Okay, so that's essentially the idea, is for both learning and for inference, when we actually classify, we only need to compute the kernel. We never need to compute phi. This is called the kernel trick. Okay, so what kind of kernels are popular? These are the ones that are implemented in sklearn. And the first one is by far the most popular. It's the radial basis function. So the first thing to keep in mind is all these kernels are just similarities. It's a way of measuring similarity between the two different input vectors, x and x prime. So the Rbf kernel just looks at the Euclidean distance squared between x and x prime, and then it exponentiates that. You multiply it by a negative gamma. Gamma is called the kernel width. It's an important parameter to choose, and then you exponentiate it. So if x and x prime are far away, then this number is large. E to a negative large number is going to be really small, and this tells us they're not very similar at all. However, if these are identical, then the norm goes to 0, e to the 0 is 1, and the largest value that kernel can take is 1. So basically, again, it's just measuring some sort of similarity between x and x prime. That's the most popular one, but there are other ones, too, that are also based on the notion of similarity. So you could take an inner product between x and x prime, again, multiply it by your kernel width, maybe add an offset r, and then take it to some power d, maybe like 2. You could, instead of this would be a polynomial kernel. Instead of that, you could use a hyperbolic tangent kernel. Those are other options. And sometimes people talk about the linear kernel. The linear kernel would be basically like doing nothing, so using no phi function at all. So the linear kernel corresponds to just the SVC, the linear SVC that we saw originally. So one of the things that's interesting about this most popular Rbf kernel is if you did try to figure out what is the phi that corresponds to the Rbf kernel, the only way to build such a phi is actually an infinite dimensional phi. You can kind of see that by expanding this exponential into this, this series here. But basically, the main point is that if you tried to find the phi that is implied by the Rbf kernel, it would be infinite dimensional. So fortunately, we never need to work with phi directly. We just work with the Rbf kernel alone, and we use that, everywhere up here. And that's very tractable, right? As you can see, it's very cheap to compute the Rbf kernel. Okay, so that's basically what the kernel trick gives us. So last thing to talk about is how we implement this in sklearn. So now we're going to use the SVC. Previously we used linear SVC. That only works, you could say, for the linear kernel. This new function, SVC, works for all kinds of different kernels. The Rbf, that's the default one, poly, sigmoid, linear, or you can specify a custom kernel of your own making. So in order to use this, you have to specify the kernel width, gamma, and you have to specify C, which controls the number of support vectors. And those two parameters kind of affect each other. So really what you should do is jointly tune them using cross-validation. Now, it is a bit expensive to do this because essentially you have to build like a grid, a two-dimensional grid of all the possible combinations of lambda and C that you want to test, and then search over that grid. And the SVC is not nearly as fast as linear regression, and so it takes a little while to run, so you have to be a bit patient. But if you have a nice big and dense grid, you can really find a great combination of parameters that's going to work well. Okay, so for MNIST, rather than going through and trying a whole bunch of gamma and C, people have already done this. So we're going to use the work from this website where they figured out that C of 2.8 and gamma of 0.0073 work pretty well. This is with the radial basis function kernel. And that's essentially what we need to do. So we instantiate that SVC, we fit it on our training data, we predict from our test feature vectors, predict our test labels, and then we look at the accuracy of the test labels. And what's nice here is that we have a huge jump in performance. Instead of 90.7, we have 97%. So all of a sudden, we're much closer to 100% accuracy. And this is where we see a huge jump in performance. And this is really why the SVM is such a famous technique in machine learning. Before we had a lot of work in the area of neural networks, the SVM was essentially the state-of-the-art technique. So basically like around 2010 or something like that. So it's a great technique, works really well. And just just one more page here. I just want to talk a little bit about some of how to deal with multiple classes in sklearn, because if you remember, we do have a couple functions. There's the linear SVC we talked about earlier, and now we talked about just the SVC alone. So when we have multiple classes, k greater than 2, as we know, one versus rest is one approach we can use. So in that case, for each class K, we separately train BK-WK pair and rather than jointly. So it turns out that the only sklearn function that supports one versus rest is linear SVC. Okay, and in that case, we're stuck using essentially the linear kernel. So we can't use our Rbf and stuff. So unfortunately, the performance of this is a bit limited. This function, linear SVC, is generally faster than the other one, but if we really care about getting great performance, this is not going to be what we want to use. We also talked about the Cramer-Singer approach, where you jointly train all your weights and all your biases together. This is implemented also only in linear SVC, which, as we know, is restricted to the linear kernel. And what you find is slightly better accuracy than this one versus rest, but it's going to be slower. So the other way that we can train greater than two classes, we talked about this briefly back in Unit 5, is called the one versus one approach. So in the one versus one approach, rather than like one versus rest, you take individual pairs of classes and consider just that pair. So for example, you might want to look at class 1 and class 2, or class 1 and class 3, or class 2 and class 3, and so on. So for each unique class pair, we'll call it K and K prime, where K is different than K prime. The idea is you separately train a binary classifier. So compared to one versus rest, where you would only need to train K, capital K, different classifiers, here you have more combinations. You have K times K minus 1 over 2. So that might sound daunting because this is something that scales with K squared. So if you have 10 classes, let's see, how many would this be? This is 10 times 9, so it's 45. So basically 45 instead of 10. So it sounds like it's more work, but it turns out that the size of the data, when you consider only a pair of classes, is smaller. And for the SVC, the complexity basically grows with the number of training samples squared. So since you have a lot less training samples when you work with 2 classes rather than all 10 classes, each of these little design problems runs relatively quickly. So even though there's more of these, the problems themselves are faster. And this approach, the one versus one, this is how Svm SVC works. And this is the approach that allows us to use a variety of kernels, but still it's a bit slower than linear SVC. The very last thing to talk about is a variation on this Svm SVC called Svm New Svc. And the only difference is that it's a reparameterization where instead of using C, you specify a different number, new, which is between 0 and 1. And new is a lower bound on the fraction of support vectors. So remember that C also controls the number of support vectors, but it's a bit hard to work with in the sense that, you just don't know what value of C will translate to a certain number of support vectors. So you just have to try like a whole bunch of C. With new, you know more what you're getting. This is going to give you a lower bound on the fraction of support vectors. So if you want like half your data to be support vectors, you could try new equals 0.5. It will, for every new, there is a corresponding C that will give you exactly the same classifier. So it's not like the quality of the classification is any different. It's just a different way of interfacing with the design. Okay, so that's it for this unit. And so at a high level, what we've seen here is that nonlinear transformations of our data are super important. We saw a huge leap in classification performance. But when we work with support vector machine, we have sort of a finite library of different kernels or different transformations that we can use. and we're not really sure which one to use for a given data set. Basically, we would have to try them all. And we're also not sure if maybe there's other transformations out there that could work much better. So that is going to be the big motivator for the next unit, where instead of using some predefined transformation or predefined kernel, we're actually going to learn a good transformation from the data itself. And that is essentially what neural networks do. So stay tuned for the next lecture.